going to do today is we're just going to summarize everything that we've done over the past 6 weeks. Okay, so differentiation and integration, they go hand in hand. They are reciprocals of each other. So just like addition and subtraction, multiplication and division, differentiation and integration, they go together. They are opposites of each other. Okay, and they are two very powerful tools of calculus. Okay? And if you guys remember back to the very first lesson we did on calculus, can any of you remember what I told you, what mathematics calculus is about?
With graphs.
It was of change. Okay? So when we're measuring change, we are usually talking about calculus. So think about the gradient of a graph. That is the change, right, between one point and the next. And the same can be said from integration. When we're working out area, what we're actually working out without even realizing it is total displacement, which is a net change of something. Okay. So let's have a look at the difference between differentiation and integration. We'll look at some of the similarities and comparisons between the two, and then we'll take a look at them each separately as well. Okay. So when we are differentiating, right, what is the result when we differentiate? What do we get? Any takers?
F dash x.
Yeah, but what do we call it? We call it something.
The derivative.
There we go. It's called the derivative. Right. And if you want to, you can also make yourself a table. Oops, and I've spelled that completely incorrectly. There we go. The derivative, okay? And when we integrate, well, what do we call it when we integrate? Okay. I'm going to preface this and say, in brackets at the top here, this is not, you don't have to write this, but I want to remind you that when we integrate, we are actually anti-differentiating.
Don't we just get the integral?
We get the integral, but there's another very special name that we always call it.
The primitive function?
There we go, the primitive. Right, or the integral. Right, let's have a look at the notation. Okay, so what notation did we use, Kiana? You just said it now. If we're talking about the derivative, what are we talking about?
F dash x.
There we go, f dash x, right? Toya, can you give me another example of f dash x? What else could we call f dash x? There were many ways that we could call it. What if I gave you the equation y equal to x squared? What would its derivative be? It would be?
Y equals to 2x.
Okay, but what would I say is equal to that? How would I tell you, how would you know that it's the derivative if you looked at it? It would have a specific thing in front of it. Instead of writing f dash x, remember, if I give you f of x, you give me f dash x. If I gave you y equal to x something, what would you tell me?
dy dx?
There we go, dy by dx. All right, and the last one could have just been d by dx if it was just an expression on its own, okay? Now, what does this all mean? Zara, can you remember back to the very first lesson I gave you on differentiation? What does f dash actually mean? It's just shorthand for something very important. Who can remember what it was shorthand for? It's one of the most fundamental things about differentiation. What is it actually doing?
Isn't it shorthand for first derivative?
Yeah, it's the shorthand for the first principle, all right? And who can remember what the first principle of calculus is? I'll give you a clue. It starts with a limit.
Oh, the limit as isn't h equals 0?
As h
Or something
tends to
equals
0.
yeah.
And then we had this, f of x plus h minus f of x all over h. And the whole point of the derivative is we said, well, we want to approximate what this thing's going to be as that tiny change in x becomes smaller and smaller and approaches 0. Right, who can tell me what the notation for the integral is?
Capital F of x.
Anyway, so we had big F of x, right? And what was the whole fundamental principle around that? What were we doing? We were
Finding the original
integrating. Yeah, we were integrating this function f of x with respect to x, right? And what do we call this, guys, Zara? Very importantly, do you notice I haven't given you any limits? So what do we call this? This is the there's no limits on this thing. So you're going to get stuck with something, the constant of instability. So this would be an,
Yeah,
this is going to be in
indefinite.
there we go, an indefinite integral. In other words, when I anti-differentiate this to find the integral or the primitive function, right, I'm going to have an infinite number of them because I'm going to have that constant, and that constant can be anything. Right? Now, we did work out that if you have an indefinite integral, you can find the definite integral by having a fixed point on the curve, right? But if you don't, we get the indefinite integral. Right, when we evaluate differential or derivatives, okay, we basically evaluate them very simply, all right? So if I ask you to find me the derivative at x equal to 2, in other words, at the point where x is equal to 2 on the curve or the line or whatever, you tell me the gradient, you simply just going to say f dash x, sorry, not f dash x, we want f of f dash 2, right? This would give me, for instance, this is just an example, okay? F dash 2 tells you, or the person looking at the problem, find me the gradient at x equal to 2. Okay? Now, who can tell me what we would do if we were finding the integral? What would I need to tell you if I wanted you to find me the integral of something? You need two very important things. You need an
A and a B.
yeah, you need a lower bound and an upper bound. Okay. There's my function f of x. Okay. And what do I have to do from this point onwards? I'll give you a clue. It's written right at the top of the table.
Integrate.
I need to anti-differentiate. Remember, integration is finding the area. Okay, I first need to find the primitive of this thing. And what is its primitive function? It's just f of x, big F of x, right? And we have it between these two boundaries, right? Now we're going to integrate by taking this primitive function between these two boundaries and subtracting their values. Okay, that gives me the area, right? What do we call this guy, Twaya? Because I don't have Charlie, what could I say about this? Is this an indefinite integral?
For the anti-differentiation.
Well, if we evaluate this integral, so if we go back to the previous where we wrote the notation, right, we had the indefinite integral, because I gave you no boundaries, no limits, right? Now I've given you two limits, right? They are just an example. They are usually written as A and B. But am I going to have a Charlie here? Is there going to be a constant of integration when I integrate between two limits?
No.
No, because area isn't some arbitrary amount of a variable.
Yeah.
Right? So this is the definite integral. And it's important that we know the difference between the two. Indefinite integral the key thing, if you notice, there are no limits next to that integral sign. Okay, there's no boundaries a and b. There's nothing. That tells me I want the indefinite integral. Right. Right, Zara. What does differentiation actually mean? So what is that f-2? What is that giving me? If I asked you for the value of the derivative at x equal to 2, what is it actually, what is that output giving you? It's giving you a very specific thing, geometrically. Well, think what derivatives are all about. Derivatives and differentiation is all about one very specific idea.
Getting as close as you possibly can
Okay, so it's giving me
to a certain point.
gradient, isn't it? And in my example, it's giving me gradient at x equal to 2. I mean, it could give you anything. If you plugged in whatever x value, you could plug in x equal to 1.7351114, and it'll give you gradient at that exact spot. Okay, so that's what differentiation is all about. It's about finding the gradient at a specific point on the curve. Okay? Right, Dominic, what about integration? What does integration give me geometrically? Right, so if you
Give
have
you the area under the graph.
here we go. There gives you the area. And in my example, it would be from x equal to 2 all the way to x equal to 5. Right? That's just as an example. Yours, in reality, it would be from A to B. Okay. Right. Finally, let's talk about the whole meaning of this. Now, gradient is a wonderful thing, but Kiana, what is gradient? What is it actually?
Changing y with changing x.
Okay, and we have a special name for that. You use it in physics a lot. It's called the, oh, what is the rate of change? Okay, who can give me a real world example of rate of change? Again, you use it every single day of your life.
When you fill up a bottle that isn't one consistent shape, it will fill up at different speeds.
Okay, but that's not something you do every day in a practical sense. Think the most basic practical example of rate of change.
You walk around from your starting
Even
point.
easier than that.
You breathe. Your lungs
When you
expand.
get in the car today and you drive, what is the thing on the dashboard of your car tell you?
Speed.
Which is just a shorthand, an easy way of saying
Distance over
Velocity.
time? Oh, velocity.
velocity. Velocity is just rate of change. Think about it. Velocity, kilometers per hour. Kilometers is the y. Hours is the x. Kilometers per hour. That's just your rate of change. So velocity is a rate of change. Okay? If we think back to when we started integration, right? I gave you the velocity and we went backwards to find the displacement over time. Okay? So if gradient or differentiation is all about what is the rate of change, what is integration all about? Who can take a guess?
Finding the displacement.
Okay, so the easiest way to say this is what is the net amount of change, right? So not the rate at which we're changing, what's the net amount of change? So if I want to know how much I've changed from 0.2 to 0.5, the integral will give me that, all right? And as Dominic has correctly said, we can just think of this as distance, or actually more correctly, displacement. We just have to be careful when we look at more practical examples in mechanics. You will see the difference between distance and displacement. Okay. Who can tell me where the difference might come in between distance and displacement? It won't always be different. Sometimes the distance and the displacement will be the same, but when could distance and displacement be different?
When you're not going in a straight line.
Okay, yes, if your velocity is negative at some point, you'll be going backwards, which means your displacement will become less, but the total distance traveled will still increase. Okay, so distance is a absolute value quantity. It can never be negative, whereas displacement can be negative because it's just in reference to your starting point, right? You can be at a negative displacement. It just means that you started backwards from where you began. Right, let's have a look at when we actually differentiated, okay? If I wanted to differentiate the most basic of functions, for instance, this, how do I use the power rule to find the derivative? What was the rule here? Okay. How do we differentiate? We drop the power down to the front.
And then you divide by the power.
No, that's integration. Okay, we drop
Or
the
you-
power down to the front and
You
then
minus 1.
we reduce the power by 1. Okay, so we drop the power and then reduce the power. Right, let's now integrate, okay, or anti-differentiate. Okay, so if I ask you for the integral, okay, of x to the power of n with respect to n, because remember this is area, it's length times breadth, what does that give me? What am I doing this time? Well,
Now you increase the power by
Very
1,
the
and
first,
then you first increase the power and then divide by that same power.
there we go, n plus 1. And who have you forgotten? Because notice I've given you no limits. This must have,
Plus Charlie.
you must have the constant of integration there, okay? If I don't give you any boundary, okay? So with this one, we increase the power and then we divide by the new power. Right, let's go and have a look at the chain rule. Okay, who can remember what was the chain rule? What did that allow us to do?
To differentiate things in brackets.
Okay, yeah, more complicated problems. And what was the whole definition of the chain rule? It was, if I want to find dy by dx, I can just change whatever that nonsense is into the bracket into something easier for me to differentiate, right? Then I can differentiate that, and if I multiply that by whatever the derivative is inside that bracket, it will give me the derivative on after. Okay. And so the process that we followed there was we differentiate the outside, then we differentiate the inside, and then we multiply together. That was the chain rule, okay? Right, we also had a reverse form of the chain rule. What was the important thing about the reverse form of the chain rule? What was the big rule about it? if we want to use the reverse chain rule? Who can remember? There was something very important about what was on the inside of the bracket.
Wasn't it that you can only do it if there isn't a power of x inside there?
Okay. In other words, the inside function has to be a linear function.
Linear.
Okay, in other words,
Okay.
there is only an x in there, and it has only got the power of 1. In other words, it's like a straight line. Okay, as long as it's a straight line inside a bracket, then it's fine. You could use this rule. Okay, and what is the integral of this? It's a x plus b. We raise the power by 1, but this time we divide by what? Well, we need to divide also by that constant in front of xa, and then also by the new power. And this is an indefinite integral. So Dominic, what do I have to remember?
C. You have to add C.
You have to remember Charlie. Okay. So those were our ways that we differentiated. Now we could have had a constant in front of these. We could have had multiple of these together, right? We learned that we can just, if things are separated by a plus or a minus sign, we can just differentiate and we can treat them completely separate. Okay. Right, let's have a quick look at differentiation. Okay, so we can have a little look at differentiation on its own. Right, because now we've kind of run out of similarities where we have opposites. Now we're kind of looking at each of these guys separately, and there were certain things that each of them did that we learned. Okay, so let's have a look at the first thing we learned was the difference between a tangent and a normal. Okay. Right. If we make dy by dx, okay, at some point x, y equal to m. In other words, remember the derivative gives me the gradient at a certain point, right? And who can tell me what's a tangent to a point on the curve? What can you tell me about its gradient?
This gradient is changing y with changing x.
There we go. In other words, if I made the gradient, if I took the derivative at a certain point and made that gradient equal to m, well, how could I find the equation for the line for the tangent? It would be y minus y1 equal to m x minus x1, right? Because the gradients are exactly the same, right? What about the normal? Who can remember what the normal was? This is the line that is.
Minus 1 over m.
Okay.
Yeah.
And what is the whole thing of the normal? It is a line that is perfectly. What is
Perpendicular.
perpendicular? Okay, so it's the line that intersects the tangent at 90 degrees. Okay, and we know for lines that intersect at 90 degrees, their gradients are negative reciprocal of each other. Okay, so there we have the tangent and the normal. Right, then we learned about increasing and decreasing functions. Right, who can tell me? If it's an increasing function, what can you tell me? What can you tell me about what can you tell me about something when it's an increasing function?
F dash x equals 0 and f
Not
The
equal to
second
0,
one.
that's not an increasing function. If it's 0, that means it's a stationary point. So for an
What?
increasing function, remember what's happening with an increasing function? Its rate of change is positive.
Yeah, well, that's what I was saying. I said f dash x is 0 and f dash dash x is negative.
No, so it's not equal to 0, right? It is greater than 0. Okay? Throughout the interval, right? Because remember, a function can vary. It can go up and down and up and down, and this will give you a certain interval where it is increasing, okay? And we can say the same thing for a decreasing function, right? A decreasing function is where the y values are getting smaller and smaller and smaller. And that just corresponds to a negative rate of change. In other words, where dy by dx is just less than 0. And that is throughout the interval as well. Okay, Kiana, we're coming to your one now. Here we go. If we have stationary points, stationary points.
That was for max and minimum points. Sorry, I'm being.
There we go. You were thinking of minimum and maximum, okay? This is where dy by dx is equal to 0. Stationary point is where we have no rate of change. The rate of change is 0, okay? This gave us two very important things. The first thing it gave us were turning points, right? And you were describing to me one of these turning points. This was, say, a maximum turning point, right? What does a maximum turning point look like? Well, it's
When dy by dx equals 0 and d squared y over dx squared equals a positive value.
there we go. So this would be less than 0 for a maximum point. And I've drawn there for you what's happening. The graph is increasing, it's stopping, and then it's decreasing. See, it's going to the top of a hill. That is a maximum point, right? Conversely, if we are thinking about a minimum point, we are decreasing just before the point. Then we're at 0 when there's no change. And then we're increasing again. This was a minimum point. And the second derivative there was greater than 0. Okay, that was the test. Right, what was the other type of stationary point that we get?
A point of inflection.
There we go, point of inflection. Okay, and who could tell me what the gradient around a point of inflection was? There was one of two. It was either positive, or it was negative to negative. In other words, the graph got to a point, it stopped, and then instead of turning around, it just decided that actually I like the way I was going, I'll just keep going in that direction. And that was a point of inflection. Right, and the final thing we learned was this idea of having a connected rate of change. Okay, so the idea was, right, and I'm gonna leave it out for a second, is that if we have two variables, right, and they can be anything, but we can just say x and y, for instance, and they are both connected by a third variable, we can connect them using the chain rule, okay? Who can remember the chain rule for this one? This was just if we want dy by dt, all right? Usually that's the way we want to express something in terms of time. So if we want a change in y with respect to time, and we are given certain information like a change in time or change in y with respect to x, and we know change in x with respect to time, we can find the connected rate of change. Okay? And we also learned that sometimes if we want dx over dy, that's just the reciprocal of dy by dx. Because using basic understanding of fractions, that x pops to the front. So there we had our differentiation. All right, everybody happy with that so far?
Yep.
Okay, let's have a look at integration. Okay, integration, right? We had some key ideas with integration that we learned. Okay, and one of the first things we learned about integration was that it's the reverse of differentiation. In other words, if the derivative of f of x is equal to f of x, then the integral of f of x is equal to big F of x plus c. And we used this definition when we were using a function and we were differentiating it in order to anti-differentiate a more complicated compound function. Okay, that if we differentiate something and we anti-differentiate it, they give us the same result. Okay. Right, and then we learned a very important thing for definite integration. Okay, it was pretty much the fundamental theorem of calculus, and that was that, guys, if we cut out, just log back in for a second, we're almost done. Okay, if we have the integral from a to b of f of x with respect to x, we learned that that's exactly the same as taking the primitive function between the same boundaries, and what we were doing is we were taking the upper bound and subtracting the lower bound, and it gave us the same thing. This is pretty much the fundamental theorem of calculus right here. Okay, so very quickly, we were looking at area, okay? So if the area, in my case A, is bound by curve, the x-axis, x equal to A and x equal to B, right? If I want to find the area, it's the same as taking the integral from A to B of f of x with respect to x, right? Another way of looking at this is just taking the integral from A to B of y d of x, right? Because f of x and y are exactly the same two things, okay? So that was the area under a curve with respect to the x-axis, okay? But we also learned that we can do the same thing so if the area is this time bound by the curve, the y-axis, y equal to A and y equal to B, right? We needed to change our equation into something different. So the area this time was the integral from A to B of f of y this time, because we need an equation x equal to, and this was with a tiny change in y, okay? Or alternatively, we could say the area was equal to the integral from A to B of x by d of y, because we needed an equation x equal to something. All right. And finally, we had the area between two curves, okay? And if we wanted to find the area between the two curves, if the area is bound by, right, we can have f of x and we have g of x as well. The area can be given as the integral from a to b of f of x, take away g of x, right, with respect to x. Okay? And very importantly, this is where a and b are points of intersection. There we go. That was it. That was basically what we learned. And when we learned volume, that was just a play on area where we learned to take the concept of area and rotate it around one of the axes. Okay? I've also got some notes on that for you. It will be in this that I'm going to link up to Edmodo for you. But that was the most important concepts that we learned throughout differentiation and integration. So hopefully you followed along there, right?